And when I say internuclear distance, we actually call this R here. It's kind of ironic that we put this in the same lecture as we talk about atomic radii, which we also call R, but they're two different R's, so you need to keep them separated in terms of what you're talking about. When we're talking about R for internuclear distance, we're talking about the distance between two different nuclei in a bond, in a covalent bond. So if we look at this graph where what we're charting is the internuclear distance, so the distance between these two hydrogen atoms as a function of energy, what we are going to see is a curve that looks like this. This is the general curve that you'll see for any covalent bond, and we'll explain where that comes from in a minute. I want to point out that the zero energy is defined as when you have a naked proton where the electron is popped out. That's what we've defined as zero energy up to this point when we're talking about single atoms. So for starters, we'll keep that as our zero energy. We're going to change it soon to make something that makes more sense in terms of bonding, but we'll keep that as zero for now. So we see that the two H atoms separate have a certain energy that's lower than when the electron's not with the atom. And then even lower down, we have our bonded hydrogen molecule. So we can think about the different kinds of interactions that are taking place. I said what holds a bond together, what holds two atoms together, is the attractive force we have between each electron and the other nucleus. That's the huge force that we're talking about in terms of making a bond stable. But there are also repulsive forces. So you can imagine we're going to have electron-electron repulsion between the two electrons if we're bringing them closer together. And the real killer is if we get too close, we're even going to have nuclear-nuclear repulsion between the nuclei of the two atoms. So this makes this chart shown in pink make a lot more sense, because if we're way out at very far distances, essentially what we have here is we're talking about two separate atoms. They're not interacting at all, so that's why the energy is the same as that for two individual atoms. That's what we're dealing with. As we get closer together, we start to get lower and lower in energy. The reason is because the predominant force at this point is going to be the attraction that's being felt between the nuclei and the electrons in each of the atoms. At some point, you're going to hit a well here, which is the point where it's most stabilized or at its lowest energy. So when we think about a bond length, this is going to be the length of our bond here. That makes sense because it's going to want to be at that distance that minimizes the energy. But as we keep getting closer, even though as we get closer, the attraction is going to get stronger between the two nuclei and the electrons, we're also going to start to have the repulsive forces become more prominent here. And in fact, they take over at some point, becoming the more prevalent of the forces. So as you get closer, the electron-electron repulsions and eventually the nucleus-nucleus repulsion is going to mean that your energy is just absolutely skyrocketing. So it just keeps going up and up as you get closer to zero here.